The dish of this radio telescope is shaped in such a way that the incoming radio waves bounce off the surface and are reflected into the receiver mounted at the front. The shape of the dish is a paraboloid of revolution. In other words, if you take a cross-section of the surface, the curve you get is a parabola. The parabola is an example of a family of curves called conics. It's one of the 3 types of conic, all of which occur in real life. The ellipse is a second type. In the solar system, the planets move around the sun in ellipses, with the sun at one focus. This is also true of most comets, although in this case, the second focus is a long way away. And the ellipse is very elongated. A few comets do not stay in the solar system. They escape into interstellar space. Austin's comet is one of these. It passed round the sun in the spring of 1990 and will not visit us again. Instead of an ellipse, its path is a hyperbola. At least it's one branch of a hyperbola. As you know, a hyperbola has 2 branches. In this program, we're going to explore an interesting property shared by all 3 types of conic. It's called the reflection property, and it has many practical applications, for example, in astronomy. But first, let's get a precise description of the 3 conics. Remember that one way of defining conics is in terms of distances. The distances from a point P of the curve to a fixed point, the focus, and from P to a fixed line, the directrix. For a conic, the distance PF is a constant multiple E of the distance PD. E is called the eccentricity of the conic. The value of E determines the precise shape of the conic. For example, for this particular ellipse, the value of E is 2/3. That is, PF is 2/3 of PD for all points P of the ellipse. In fact, every value of E less than 1 produces an ellipse. Ellipses are symmetric in both axes. And this means there's a symmetrically placed second focus, F dashed, together with its own directrix. So that's the ellipse. Now for the parabola. This time, the value of E is 1. That is, every point P of the parabola is equidistant from the focus and directrix. Notice the parabola has only one focus. Finally, let's look at the hyperbola. For this particular hyperbola, the value of E is 3/2. The equation PF equals 3/2 PD also describes points on the other branch of the hyperbola. In fact, every value of E greater than 1 produces a hyperbola. Hyperbolas are also symmetric in both axes, so there's a second focus together with its directrix. So that's the 3 types of conic. Let's now see how the shape of the conic varies as we vary the value of E, starting with our ellipse. Let's decrease the value of E from its current value of 2/3. Watch the foci as well as the ellipse. The ellipse gets rounder and the foci get closer. At E equals 0.3, The ellipse is so round, it's difficult to distinguish it from a circle. But notice the foci. If this were a circle, the foci would coincide at the centre. So the circle is the limiting case of the ellipse as e tends to 0. By the way, the Earth's orbit has eccentricity 0.017, so it's very close to a circle. Let's now increase e, and we'll take it to the value 1 and beyond, so as to see the transition between the three types of conic. This time, we'll keep the left-hand focus fixed, together with its directrix. Watch the right-hand focus as well as the ellipse. The ellipse has stretched much more horizontally than vertically. Also, the second focus has moved a long way to the right. In fact, as e gets closer and closer to 1, the second focus disappears off towards infinity. So the parabola can be thought of as a very elongated ellipse with its second focus at infinity. Another thing to contrast is the curvature on the left. The parabola curves around the focus less sharply than does the ellipse. The parabola is a shallower curve. If we increase e further, we'll get yet shallower curves, hyperbolas, which get more and more shallow. And there's something else that happens. On the left, together with the second branch of the hyperbola, the second focus reappears. Incidentally, the hyperbolic orbit of Austin's comet has eccentricity about 1.0003, so its orbit is very nearly a parabola. So that's the relationship between the three types of conic. We can now explore the reflection property which I mentioned earlier. Let's start with the ellipse.
Here's a vertical mirror which we've curved into an elliptic shape. I've marked the two foci, and if you look directly from above, you can see that I've aimed each of these three torches to send a pencil beam of light through the right-hand focus. Incidentally, only the top half of this ellipse is silvered. That's why there are no multiple reflections. So all three beams pass through F' and are then reflected to pass through the other focus, F. In fact, this will always happen. A ray of light passing through one focus is always reflected to pass through the other. Now, how can we prove this reflection property? What do we need? If a ray of light hits a mirror at a certain angle, what's the angle of reflection? For a plane mirror, the ray is reflected at the same angle as it approaches. The yellow angle equals the green one. In fact, the same is true of a curved mirror. But this time, the angles have to be measured from the tangent at the point of incidence. So to prove our elliptic reflection property, we need to show that if you take any point P and join it to F and F', then the angles these chords make with the tangent are equal. One way of showing this depends on a further property of the two foci. If we add the two focal distances, we get E times PD plus PD'. But this is the same for all points P, because it's E times the fixed distance from one directrix to the other. So PF plus PF' is constant. We can use that focal distances property to draw an ellipse using a piece of string. I've attached it to 2 points, which will be the foci. And as I draw, the sum of the focal distances is the length of the string, which is fixed, and so this shape must be an ellipse. And I can use this string construction to prove the reflection property of an ellipse. First, let me swing the drawing board up until it's vertical and the string hangs freely. and I'll rotate the board through some angle. I'm going to use this pulley as a plumb line. The weight makes this bar hang vertically under gravity so that the crosspiece is horizontal. So let's see what happens if I let the string hang freely and release the pulley. The pulley rolls under gravity to its lowest possible position. In other words, it comes to rest at a local minimum of the ellipse curve. So this horizontal crosspiece must be a tangent to the ellipse here. Now, how does this help to show the reflection property? How do I know that the angle between the string and the tangent is the same on both sides? Well, the string must have the same tension throughout its length. So the plumb line is being pulled with equal force in this direction towards F' as it is in this direction towards F. But the pulley is at equilibrium here. So in particular, the net horizontal force on it must be 0. Well, we've noticed that these two forces towards F' and towards F must be equal. So for them to balance horizontally, they must act at equal angles to the horizontal. So that's proved our reflection property at this point on the ellipse. The two focal chords make equal angles with the tangent. And finally, suppose I rotate the ellipse. The pulley rests at every point on it in turn. And at each point, the ellipse has the same reflection property. These two angles are equal. By the way, what do you think would happen if the bottom half of the ellipse were also silvered? Well, it is actually, but we've been covering it up. As you might expect, the beams passing through F are reflected again to pass through F', and in fact they're reflected yet again to pass through F and so on, but the beams are rather faint after the second reflection. Now let's look at a parabolic mirror. Eleanor said earlier that the same reflection property holds. A light ray coming from one focus will be reflected to pass through the other focus. But remember, the parabola is the limiting case of a very elongated ellipse whose second focus has gone off to infinity. So if light rays came from that focus, they'd be parallel rays. We've shown only the ones above the axis for simplicity. And as promised, they're reflected to pass through this finite focus. That's why this point is called a focus. Parallel rays are focused through it. In fact, we started the program with an application of this principle.
We were considering radio waves instead of light waves, but the principle is the same. The waves come from very distant objects and reflect off the parabolic dish to pass into the receiver at the focus of the dish. The radio waves are converted by computer into images of the distant object, in this case the galaxy NGC 289, 100 million light years away. We'll come back to another design of telescope later, but first, what about a mathematical proof that this reflection property does indeed hold for every ray parallel to the axis? We can construct a proof if we know the equation of the tangent at any point of the parabola.
I'll derive the equation, then Eleanor can finish the proof. I'll use these parametric equations for the parabola, where x and y are expressed as functions of a parameter t. That is, each point x, y in the parabola has coordinates at squared 2at for some value of t. The constant a is the x-coordinate of the focus. Now, once we have a curve in parametric form, how do we find the gradient of the tangent at a point t on it? Well, the gradient of this chord between the points t and t plus delta t is the height of this triangle divided by its width. So the gradient of the tangent at t is the limit of this expression as delta t tends to 0. Let's divide top and bottom by delta t. And if we take the limit, we get y dash t over x dash t. Right. Now let's use this formula for the gradient of the tangent to find the equation of the tangent at a point on the parabola. Here, y of t is just 2at. So y dash of t is 2a. And because x of t is at squared, x dash of t is just 2at. So the gradient of the tangent is 1 over t. Now, the tangent goes through the point at squared 2at, so its equation must be y minus the y-coordinate of that point over x minus the x-coordinate equals the gradient of the tangent 1 over t. And if we cross-multiply and rearrange, we get the equation ty equals x plus at squared.
I can now use this equation of the tangent to prove the reflection property. What I have to prove is this. Consider the line FP and the line through P parallel to the x-axis. I have to show that the tangent makes equal angles with these two lines. Well, alpha equals this angle gamma because these two lines are parallel. So I only need to prove that gamma equals beta. To do this, I'll show that the triangle APF is isosceles. That is, the side FP equals the side FA. This is the problem we asked you to do before the program. FA is just FO plus OA. Well, FO is the x-coordinate of F. And to find OA, we need the x-coordinate of the point A. This can be calculated from the equation of the tangent. At the point A, y is 0. Therefore, x is minus at squared. This means the length OA is at squared. So that's FA. And I need to prove that FP is also a plus at squared. Well, FP squared is the x-coordinate of P minus the x-coordinate of F, all squared, plus the difference of the y-coordinates, all squared, which works out to a plus at squared, all squared. So FP does equal FA, and hence beta equals gamma, which equals alpha. And that finally proves the reflection property for the parabola.
Let's take another look at the reflection property in action. You've seen light coming from the focus at infinity, parallel rays being reflected through the finite focus. But what about the reverse? What if a ray comes from this finite focus? Well, these three rays are coming through here, but I've been covering up the bottom half of the mirror so they're not reflected. If I uncover it, the rays are reflected parallel to the axis, out towards the focus at infinity. This idea has obvious applications. Light from the finite focus reflecting out in a parallel beam. Anti-aircraft searchlights in the Second World War had parabolic reflectors. And the light source was positioned at the focus of the parabola, hence producing a parallel beam. It's interesting to relate these two different examples of the reflection property to the different curvature of the conics.
For the parabola, light from the focus is reflected in parallel rays towards the focus at infinity. But if we reduce the eccentricity of the conic to get an ellipse, the ellipse curves more sharply around the first focus and so reflects light inwards to converge on the second focus. Conversely, if we increase the eccentricity, we'll get a hyperbola, which is a shallower curve than the parabola, so the reflected rays diverge.
But we can say more than that. The divergence is very precise. What happens is that light rays from F reflect outwards as though they have come from the other focus F'. That is, for any point P, the tangent makes an angle with FP, which equals the angle it makes with F dash P. This is called the internal reflection property and is essentially the same as the property we've seen for the other two conics. Also interesting is the external reflection property. That is, if you silver the outside of the hyperbola and aim a beam at F, it reflects to pass through F dash. This follows directly from the internal property. The first external angle is opposite the green internal one, so it's equal to it. And the second external angle is equal to its opposite yellow angle. And since the two internal angles equal each other, so do the two external angles.
This external property is actually employed for optical telescopes. This is the 4.2-metre William Herschel optical telescope on La Palma in the Canaries. Let's first summarise the way it works, and later we'll look in more detail at a cross-sectional diagram. 4.2 metres is the diameter of the mirror being uncovered at the moment. This is one of two mirrors. It's the primary mirror, and it's parabolic, just as in the radio telescope. So parallel light rays are reflected to pass through the focus. At least they would be if the secondary mirror were not in the way. This is a hyperboloid of revolution, and its near focus coincides with the focus of the primary mirror. So by the reflection property, light rays which are aimed at the hyperboloid's near focus are reflected towards its far focus, and there's a hole in the primary mirror for the light to pass through to the far focus. It's much easier to attach instruments at this point, which can be reached from the observing platform, than at the primary focus. Let's go through that more carefully with a simplified diagram. The mirrors are positioned so that the focus of the primary coincides with the near focus of the secondary. Incidentally, here's where the second branch of the hyperbola would be. And here's the far focus of the hyperbolic mirror. Parallel light rays from a distant object are reflected by the parabolic mirror towards its focus, but the rays are intercepted by the hyperbolic mirror and reflected towards its far focus. And they pass through a hole in the primary mirror to meet at the far focus. Well, we've come a long way in this programme. In the first part, we thoroughly explored the variation in the shapes of the conics.
And despite that variation, we saw how the reflection property holds for all three types of conic. Light from one focus is always reflected in the direction of the other focus.
And we looked at some important practical applications of this property.